So, very good evening to everyone. So, I am Rohit Gahlot and I will be taking the week two's doubt clearing session. So, in the week two, majorly the different types of microscopy like bright field microscopy, phase contrast microscopy, polarization microscopy, dark and bright field microscopy, and opaque microscopy were taught by Professor Sankaran. And further, if we in brief, like I will be giving a brief discussion on the difference between all these microscopy, followed by we will be solving some problem and problems like MCQs and numericals both, and then we will be wrapping off. So firstly, if we talk about the opaque microscopy, so in this microscopy, it was for the non-transmitting specimens, and also the illumination is in this microscopy. The illumination was from the specimen, and reflected light is collected by the objective lens for uh, the observer, and contrast is also achieved through the changes in the reflectivity or surface texture of the specimen. So generally, the opaque microscopy is for the non-transmitting specimens. Okay, and now if we move to the bright field microscopy, so we can say that it is a general purpose technique for visible specimens, and also this is the most common form of the microscopy. And here the specimen is illuminated with a bright light source, and specimen appears darker against a bright background. Okay, so generally the this is general purpose microscopy. Now if you move to the polarization microscopy, so this is for the bifringent materials. Okay, and also it is this microscopy is to observe transparent or low contrast specimens such as living cells without the need for staining. Okay, and it also enhances the contrast of the phase difference in the specimen by converting them into difference in brightness or intensity. Okay, and also it achieves this by creating interference pattern between the direct and reflected light passing through a specimen. So, and also this was the this is the schematic of the polarized light microscopy which I was just talking about. And for, and so here also the polarized light to examine the specimen is utilized, and it has its electrical the polarized light has its electrical vectors oriented in specific direction, which interacts differently with the material depending on their optical properties. And also to study, like generally this is to study the bifringent materials such as crystals or biological tissues. Okay, so in short, if we uh, like uh, so if we talk about the opaque microscopy, so this is for non-transmitting specimens. Then this is for the general purpose technique for visible specimen. If we talk about the polarization microscopy, this is for the birefringent materials. And if and phase contrast. So this enhances your contrast in the transparent or low contrast specimens. Okay. So I have one question now. So the dark field, if we talk about the dark field microscopy also, so that is also for non-transmitting specimens. And what is the difference between the dark field and the opaque microscopy? Anyone? So if we talk about the dark field microscopy, so generally the difference is between their uh, what we say. So generally the illumination is different. They both these employ different illumination techniques, and contrast mechanism is also different. So with this, so these two differences make them suitable for different types of specimen and applications. Okay. So like in the dark field, oblique or off axis illumination is utilized, and generally their application is for studying about the bacteria and all. While the opaque is the direct illumination from above the specimen is utilized, and with that reflect light is observed. This is generally for metals and coatings. Okay. So these are the in brief the difference between all these microscopy which were taught in the week 2. Okay. So now let's move to some of the problems. Or okay, so let's move. So these are simple MCQs. So the first one is the which of the following statement is incorrect for the opaque stop microscopy techniques? Option A, also known as sensitive dark field microscopy, an inclined option B, an inclined surface can be easily seen. C, stops the diffracted beam by using a phase plate, and D, the background of the image looks dark. So which is the incorrect one? So this is also known as the sensitive dark field microscopy. This is the true. An inclined surface can be easily seen. Yeah. Uh, stops the diffracted beam by using a phase split. No, this is not the, because this is for some other microscopy. And then the D is the background of the image looks dark. No, yeah, that is also true. Now, moving to the problem number 2, the action of the phase plate in the phase contrast microscopy is to make a both S and D wave advance by lambda by 4. Only the S wave advances by lambda by 4. C, both S and D wave is retarded by lambda by 4, and D, S wave advances by lambda by 4 and D wave retarded by lambda by 4. Yeah, that is the right answer. Now the third one is the, this is also, this problem, third one is taken from directly from the like recordings also. You can see the professor Sankaran taught this in the class. So a ray of designated wavelength passing through lambda by 4 retarded plate shows which type of waveform? Anyone? So for the lambda by 4, this will be the circular one. Okay. So, and fourth one is, which among the following is used to split polarized ray into the ordinary ray and extraordinary ray? So this is quartz. This is a birefringent material, so this is the correct answer. So the fifth number is, two specimens having the same thickness but different refractive indexes N1 and N2. Which of the statement is correct for phase contrast microscopy? Both specimen have the same contrast. Specimen 1 have a higher contrast, specimen 2 have higher contrast. So we know that the relation between N1 and N2, we talk about the optical path length. So we can write it as S minus N0. Here N0 is fixed, then it's multiplying by T. N0 is fixed, so whichever have the higher refractive index will have the higher contrast. So B is the correct answer. Moving to the sixth, the contrast in the differential interference contrast microscopy is generated due to A, the gradient in optical path length, B, optical path length, C is the bonding in the material, and D is the crystal orientation. So the correct answer will be the gradient in the optical path length. Okay, and the contrast in the is generated due to the gradient in the optical path length. Okay, so moving to the next problem, which of the following statement is not true for phase objects? So A, alters the velocity of an emergent ray, B, shift the phase of an emergent ray, C, change the amplitude of the emergent ray, and D, the energy of the beam remains the same. So yes, it changes the amplitude of the emergent ray. Which of the following statement is correct? Both ordinary and extraordinary follow Snell's law. Wrong. Both ordinary do not follow. Wrong. Ordinary ray follows Snell's law, while the extraordinary ray does not follow Snell's law. Yes, this is the correct one. Which of the following statement is not true for dark field microscopy? The background of the image looks dark. It's not true. Yeah, this is the true, but this is the true one. All the features looks bright. Only the oblique beam is allowed pass through. Only the central beam is allowed pass through. Yeah, D is the correct answer. This is not true. So now moving to some of the numericals. So let's say you have a phase contrast microscope where the phase plate produces a phase shift of lambda by 2 is a 90 degree, and if the wavelength of the light used is 550 nanometer, what is the phase difference in the degrees? So here we can solve this as, so here we can write as the phase shift is lambda by 2, Okay, and then your phase shift is given by, so your phase shift is given by so your phase shift is lambda by 2. So we will put it as here. So lambda by 2 is equal to 2 pi times your delta n times t divided by your lambda, which is around 550 nanometer. So from this we can find out the delta n times t, and then so your delta n times t, this we will be getting as lambda by 4. Okay, and then if we try to find the difference between your delta n, that is the difference between the refractive index, it will be coming around 34 or 35, between 34.37 exact. So we can say that the refractive index of your specimen relative to the surrounding medium is around 34.37. Okay, now moving to the next problem. So in a culture of cells observed under a phase contrast microscope, if the average thickness of the cell is 10 micrometer and the refractive index of the cell relative to the surrounding medium is 0.2, what is the phase shift experienced by the light passing through the cells? So this is also the similar type of problem. So the thickness of your cell is 10 micrometer, and then your delta n is 0.2. So from here we can find your phase shift easily. So this will be given as 2 pi delta n times t divided by lambda. So when we will be solving it, we will be getting as 2 pi times 0.2 multiplying by your thickness is 10 micrometers. I am converting it into meter. Then it will be divided by your lambda, which is around, so taking it same as the previous question, so 550 it is nanometer it was. So this will be coming around 22 radians, 22.92 to be precise. It can be converted into degrees also. I'm multiplying by 180 by pi, so it will coming around 1313 degrees. The next problem is that suppose we have a calcite crystal with a thickness of 2 mm. A beam of unpolarized light enters the crystal at an angle of incidence of 30 degree from the normal. Calcite has an extraordinary refractive index of about 1.658 and an ordinary reflective index of about 1.486 for the yellow light. The angle of reflection theta for the ordinary and extraordinary ray will be. So we know that uh, one of them will be following the Snell's law while the other won't be following the Snell's law. So for the ordinary one, we can write as the n1 sine theta 1 this will be equal to your n2 sine theta 2. So we can solve n1 is the outside the crystal, which can be taken as air, and your sine theta 1 is 30 degree, which can be equated as n2 is your calcite, so it is given as 1.65 8 times sine theta 2. From here we can find out the theta 2 values. So this will be coming around 21.32. So if we talk, this is for the ordinary way, and if we talk about the extraordinary, this won't be following your Snell's law. So if so we can say that if it will be like propagating perpendicular to your crystal phase, and it will be exiting at the same angle, like it was incidence angle was 30 degrees, so it will be like reflect exit or reflect at the 30 degree itself. Okay, so now moving to the next problem. So suppose we have a birefringent material with an extraordinary refractive index of 1.7 and an ordinary refractive index of 1.5. A beam of light passes through a 1 mm thick slab of this material, and we need to find the birefringence and the phase retardation. So this is directly, we know that the difference between these two refractive index. So this can be written as Ne minus NO, which can be equated as 1.7 minus 1.5. So this will be coming as 0.2, and a beam of light passes through 1 mm thick slab of then the phase retardation we also need to find. So this is like similar to the what we are doing from the last two problems. So 2 pi delta n times t divided by lambda, and then if we will solve it, we will be getting as 2 pi times delta n is your birefringence is your 0.2, your thickness is 1 mm, and your delta is around lambda. Again, it is taking as for the green light, that is 500 nanometer. If we will convert the unit conversion, and then all finally we will be getting around 8 pi radians. Okay. Suppose we have a microscope objective with a numerical aperture of 1.4, and we want to use it to observe a specimen with a refractive index of 1.52. To achieve maximum resolution and brightness, we use an immersion medium with a refractive index of 1.158. So we know that the numerical aperture in case of your uh, effective uh, that is the effective numerical aperture in case of a presence of immersion or some media, it can be write as n times numerical aperture of the previous one. So n is your effective effective index. So this will be your the refractive index is 1.518 times your numerical aperture is 1.4. Okay, this will be coming around 2.12 in case of your immersion. So from this we understand that your resolution is proportional to the, so I can write it as your that your resolution is proportional to your numerical aperture, right? And with immersion, your numerical aperture increasing, so your resolution is directly also increasing. And if we talk about the brightness, so this also increases with your immersion media. So brightness also increases when immersion medium is used, because as your numerical because your increased numerical aperture will allow more light to enter, your objective lens which will result in your brighter image. Okay. Now if we move to the question number 16, suppose we have a metallic sample with a rough surface that we want to examine using opaque microscopy. We want a microscope with a magnification of 100 times and an objective lens with a numerical aperture of 0.65. The illumination source is providing a wavelength of this, and we need to find a resolving power, field of view and depth of field. So firstly, what are these? The field of view and depth of field. We already studied that the field of view is the area of your specimen visible through your eyepiece. It also depends on the magnification of your microscope and diameter of your diaphragm, right? And if you talk about the depth of field, we discussed that this is the range of distances from your objective lens where your specimen appears to be in the focus. Okay. Now if we talk about the firstly the opaque microscopy is written. So here generally your specimen is opaque, that is it doesn't transmit light. Instead it reflects, absorbs or scatters. And further, the opaque microscopy is to study about the surface features, textures, or the deflection behavior of the behavior. This is already we discussed in the recorded videos. And if you talk about your resolving power for this, so this will be a function of your numerical aperture and your light, numerical aperture and your illumination source, which is your lambda. This is dependent on these two. And further, we resolving power, we can write it as 0.61 times lambda divided by your numerical aperture. Okay, and after solving this we will be getting as 0.61 times your lambda is your 550 nanometer divided by your numerical aperture, and the numerical aperture is 0.65. So when we will be solving it, we will be getting around the resolving power of around 0.571 micrometer. That means your that means for this particular numerical aperture and wavelength, your microscope is able to resolve around 0.571 micrometer. Okay. And if we talk about your field of view, so as I just discussed that this is your area of specimen visible through your eyepiece, right? It depends on your magnification of a microscope and diameter of the diaphragm. And for this is your first one we can say. And if we talk about your field of view, so your field of view for 100 times of magnification of your objective lens, this is around 0.2 mm. For 200 micrometer or 200 micrometer. And if you talk about your depth of field, this is around 1 micrometer. For opaque microscopy, depth of field is generally less than your transparent specimen. So for your opaque microscopy, your depth of field is generally less compared to your transparent specimens. Okay. So these were some of the problems which I wanted to discuss. So if anyone has any doubts regarding that, we can discuss this. Okay. Okay, then I think as there are we should I think I should wrap up the session then, because majorly these were the problems I wanted to discuss in this session, but there are no students, so okay then. So very good afternoon to everyone. So I'm Rohit Galat and I will be taking the week 11's material characterization tutorial course. So in the last day we talked about basics of the TAM, and from the TAM diffraction what can be inferred. So we were discussing about that in detail. So we discussed that phases and crystal structure types, crystal symmetry and space groups, orientation relationship between phases, determining growth direction, interface coherency, defect identification, example, twins, dislocations, ordering behavior of crystal structure and the site occupancy preferences. These are the things that can be determined from the TM diffraction. So now the question comes, why the electrons only? So anyone would like to answer that? So the ability to resolve the tiny objects improves as the wavelength reduces. We already know that from the week 1 class, week 1 lecture. So let us consider the microscope objective. Okay, so these are the objects to be resolved. So having distance between the D, and then this is the focal length of the lens if image plane is at a large distance. And then so then we determined that the critical angle for resolution is given by 1.22 times lambda by d. So the minimum d for which we can still resolve two objects is AC times the focal length. Okay, so d minimum is approximately f alpha AC. Then it can be written as 1.22 lambda f by d. So a good microscope objective has f by d is around 2. So with lambda around 500 nanometer, the optical microscope has a resolution of around 1 micrometer. Okay, so let's continue continuing on that. So the resolution of the electron microscope. So firstly, we know that the it behaves as a light as well as a matter. So behaving like a light, it can be as h by lambda. Matter also it can written as, so, and P is E by capital E by C. Then energy can be given as hc by lambda, and for if you consider it as a matter, then energy can be written as h square by 2m lambda square. So the for the wave behaviors, images and diffraction patterns, wavelength can be turned by energies. And for the charged particle behavior, strong electron specimen interaction, then the chemical analysis is possible. Okay. So typically electron beam current in TEM is around 0.1 to 1 microampere, which corresponds to 10 to the power 12 electrons passing through the specimen plane. So with around 100 kilo electron volt energy, these electrons travel at about 0.5 c, approximately 1.6 times 10 to the power 8. So they are separated by 0.16 centimeter. This means that there is never more than one electron in the specimen at any one time. And further, the electron diffraction and interference occur, both of which are wave phenomena and imply interaction between the different electron beams. Now for the fundamental constant and definition, we talk more about the electrons. So the charge is given by 1.6 times 10 to the power minus 19. 1 electron volt is around 1.602 times 10 to the power minus 19 joule. So the rest mass is around 9.1 and 10 to the minus 31. Then the rest energy can be calculated and followed by the kinetic energy. The Planck's constant we know, then 1 ampere. So the speed of light in vacuum is around this. Okay, so the de Broglie wavelength of an electron can be given as lambda is h by p, and then the relation between the electron's wavelength and its kinetic energy E. So P and E are related through the classical formula, we know that. So E is given by P square by 2m, where Me is 9.11 times 10 to the minus 31 kg, and energy can be given as h square by 2m lambda square. So h is uh, 4.14 times 10 to the minus 15 electron volt second, and we can calculate E as 1.505 eV nanometer square by lambda square. So don't confuse this with for energy of photons, which is given by 1240 eV by lambda. And for electrons, it is given by 1.505 eV nanometer square by lambda square. So let's solve an example. So we wish to observe a virus with a diameter of 20 nanometer, which is much too small to observe with an optical microscope. So calculate the voltage required to produce an electron de Broglie wavelength suitable for studying this virus with a resolution of d minimum around 2 nanometer. The f number for an electron microscope is quite large, so f by d is around 100. So try to solve this and we will discuss about it. So we can solve it by d minimum is 1.22 times lambda f by d, and then we can so we find out that the lambda is around 0.0164 nanometer, and similarly we can we can calculate energy as 5.6 kilo electron volt. So that means to accelerate an electron to an energy of 5.6 kilo electron volt requires around 5.6 kilovolts. Now there is one more thing like I want to cover. So we discussed briefly about the SAED pattern in the last class, so we'll discuss about indexing SAED patterns. So firstly we select the central spot. After selecting the central spot, we measure the distance between central spot and other nearest spots. This gives the uh, so so this gives the inverse of the d spacing 1 by d for a particular HKL. Now take the ratio of the distance measured. Compare the measured ratio with the expected from the table 1 given below. Now start giving the indices for matching ratios as given in the table. Now cross-checking the indexing by measuring the angle between vectors joining the central spot and the other spots using the following equation. Now find the zone axis using any of the two indexed HKL, and then make sure that all the indexed HKL satisfy the zone law. Okay, so here I summarized for in table for all the details for you. So like these are the some examples, simplified examples for you. So pattern 1, pattern 2, pattern 3 and pattern 4, and then these other, so you can all try these and you can